All right, welcome to The Explainer. Today, we are diving deep into Tauri. Now, this is a framework that's making some pretty big promises about how we build desktop apps. And hey, if you're a web developer and you've ever thought, man, I wish I could build lean, fast, native apps without having to learn a whole new world, then you're in the right place. Let's get right into it.
So, let me ask you a question. What if you could build a really powerful, super secure desktop app, for Mac, Windows, and Linux, using just the stuff you already know? I'm talking HTML, CSS, JavaScript. That's it. It sounds kind of too good to be true, doesn't it?
Well, believe it or not, that is the central promise of Tauri. It's this framework that lets you take all those web dev skills you've spent years honing, whether you're a React person, a Svelte fan, a Vue enthusiast, whatever, and it lets you wrap all that goodness into a native shell. And the best part? It's incredibly small, blazing fast, and secure right out of the box.
Okay, so how on earth does Tauri actually pull this off? Well, to get it, we really need to peek under the hood at its core architecture. See, a Tauri app isn't just one single big thing. It's actually a tale of two processes, both working together in perfect sync.
And this separation, it's absolutely crucial. So on one side, you've got your front end. This is a WebView, and its job is to render your user interface, all your HTML, CSS, and JavaScript. You can just think of it as the face of your application. But then, on the other side, you have the backend. This is a super powerful core written in Rust, and it acts as the brain. It does all the heavy lifting, like accessing the file system, making network calls, or crunching big numbers.
So you might be thinking, okay, if they're totally separate, how do they even talk to each other? Well, they use this thing called an IPC bridge. IPC stands for Inter-Process Communication, which is just a fancy way of saying they have a special way to chat. The private phone line analogy is perfect. It's this secure, direct channel. The front end can pick up the phone and call the back end to ask for some data or tell it to do something, and the back end can call right back with the answer.
All right, let's zoom in a little bit more on that back end, because the Rust core really is the brain of the whole operation. This is where all the most important stuff lives. All your critical, performance-sensitive, and super secure logic gets executed right here.
So how do you actually expose a function from this Rust brain so your JavaScript can use it? Well, it's almost ridiculously simple. You use this thing called a Rust macro, @command. You just type that one little line of code right above your Rust function, and that's it. That's your magic word. It tells Tauri, hey, go ahead and generate all the complicated boilerplate needed to make this function available to the front end and do it securely. It just handles the entire communication bridge for you. It's awesome.
Okay, let's walk through a real-world example, something simple like a counter app. So, step 1. The Rust command gets a handle to the app's shared data, the current count. Step 2, and this part is so important for safety, it locks that data. It puts a lock on it so that nothing else can mess with it while it's being changed. And then, step 3, once it's safely updated the number, it unlocks it and sends the new value right back to the front end.
So that lock that I just mentioned, it has a name. It's called a mutex. It's short for mutual exclusion. And the bathroom door analogy is honestly the best way to think about it. Only one person, or in our case, one part of the code, can have the key and be inside changing the data at any given moment. This is what prevents total chaos and makes sure your data doesn't get corrupted because two things are trying to write to it at the exact same time.
All right, so we know the front end and the back end are chatting over that IPC bridge. But there are really two main modes of conversation they use. You've got commands, which are basically requests started by the front end, and then you have events, which are updates pushed from the back end.
Let's start with a command. A command is basically the front end asking for something. It uses this simple invoke function. So in your JavaScript code, you might say something like await invoke greet name world. This is literally your front-end code saying, hey, backend, I need you to run your greet command, and here's the name world to use. It's a very specific direct request. And then, on the other side of that phone call, in your Rust code, Tauri picks up, it finds that greet function, the one we tagged with our special @command macro. It runs the function using the world string we sent, and then it sends the result right back where it came from. It's a perfect call and response. The front end asks, the back end answers. It's really as simple as that.
But what about the other way around?
What happens when the backend needs to start the conversation? This happens all the time with long-running tasks, right? You don't want your whole app to just freeze up and wait. And that is where events come in. With events, the backend can push updates to the front end whenever it wants, without even being asked.
Okay, let's use a great analogy from the source material, a pizza oven. Imagine you tell the backend, hey, bake me a pizza, which is like starting a big file download. The Rust backend kicks off this task in the background, so your user interface doesn't freeze, it stays totally responsive. Then, after a few minutes, the backend can emit an event, like a little notification that says, task progress 25% done. A few minutes later, another ping, task progress 50% done. Finally, when the pizza's ready, it emits one last task complete. Your front end never had to keep asking, is it done yet? Is it done yet? It just listens for those pings from the oven. It's so efficient.
So, we've gone through the architecture, we've talked about the Rust core and how these two parts communicate, but so what? Why does any of this actually matter? Let's talk about the payoff, the real-world benefits you and your users get from this whole setup. This architecture really boils down to 4 massive wins. First up, security. Because you have to explicitly list everything your app is allowed to do, it's secure by default, no surprise permissions. Second, tiny bundle sizes. This is huge. Since Tauri uses the web renderer that's already on your computer, it doesn't have to pack a whole web browser inside your app. Third, native speed. All that core logic runs in compiled Rust, giving you performance that JavaScript just can't touch on its own. And finally, my favorite, freedom. You get to build your UI with React, Vue, Svelte, whatever you want, the tools you already know and love.
And look at this. This chart really puts that size difference into perspective. It's not a small difference. It's dramatic. You see frameworks like Electron, which are great, but they have to bundle an entire browser, leading to apps that are often well over 100 megabytes. Now look at the Tauri app. We're talking under 5 megs. Think about what that means for your users. Downloads are lightning fast, it barely takes up any space on their hard drive, and it uses way less memory when it's run. So really, it all boils down to this, right? Tauri gives you the power to build these incredibly lean, secure by default apps. And you get to do it all using the web skills you already have. It's the best of both worlds, truly.
And that really brings us to the big, final question. When you combine the amazing flexibility of modern web tech for the UI with the raw power and safety of Rust for the backend, you get a really, really compelling new way to build software. So the question I want to leave you with is this. Is this blend, this hybrid of web and native, the future of how we're all going to be building desktop applications?